Hi, welcome back again. We are on chapter 23 of Materials Kinetics, which is on Monte Carlo techniques, specifically Monte Carlo techniques for doing atomic scale simulations. The outline for today is we're going to cover Monte Carlo integration. What is it? How does it work? The Markov chain of states. We will do a comparison then of molecular dynamics simulations versus Monte Carlo simulations. We'll discuss Monte Carlo sampling in different ensembles and then finish up with the kinetic Monte Carlo approach. So Monte Carlo, the method was developed by von Neumann, Ulam, and Metropolis at the end of World War II to study the diffusion of neutrons in fissionable materials. The name Monte Carlo was chosen by Nicholas Metropolis because of the extensive use of random numbers in the technique. Monte Carlo, of course, referring to the famous casinos in the Principality of Monaco. So since its introduction by Metropolis et al., Monte Carlo has been used for any number of different problems in mathematics and physics, including the detailed simulation of atomic structures of materials. This shows a very basic example of what is meant by Monte Carlo integration. An example is, what if we want to find the value of pi by hit and miss integration of a circle? For example, if we've got this so this is going from -1 to 1 on the y-axis, -1 to 1 on the x-axis. So it's a 2 by 2 square. And then you've got a circle that is fitting exactly inside that square. And if you just randomly throw darts at this with random positions, some of them are going to be hits that end up in the circle. Some of them are going to be misses that end up in the square, but not in the circle itself. And one can estimate the value of pi, knowing the geometrical formula for the area of the circle divided by the area of the square. This is equal to pi over 4. And this can be approximated by the number of hits over the total number of shots. So the number of hits here would be the number of points that fall within the circle, and the number of shots would be the number of points that fall within the square, including all those points that are in the circle itself. And this can give you a pretty good approximation of the value of pi. And the greater the number of shots that you take, the closer you will get to the actual value of pi. So you'll be able to get that with greater precision with a greater number of sampling. And this is an example of Monte Carlo because it is doing a random sampling of the phase space in order to estimate some property that we want to measure, or in this case, simply the number pi. Monte Carlo integration is conceptually simple, and it often offers an accurate estimate of most integrals. And in fact, if you've got some, awful math problem that is too difficult to solve analytically, Monte Carlo methods may be a way to find a solution numerically. So let's consider, what if we have the following integral shown here? If this is the integral capital F, which is an integral of this function f of x integrated over x between the limits of x1 and x2. What we can do is multiply by this function by 1, but we multiply by 1 in a fancy fashion. So if you take this row of x function divided by the row of x function, that is 1. And this row of x is some arbitrary probability density function. So we take the function that we want to integrate, multiply and divide by the same probability density function that we're going to use for sampling. Then with the Monte Carlo technique, we perform a number of trials tau, each choosing a random number here, zeta sub tau, from that distribution. And then we can estimate this integral as being the average value over all of our trials of this function evaluated over those random numbers, zeta sub tau, divided by this arbitrary probability density function, zeta sub tau. So we're sampling it on that probability density function and then dividing out that probability density function to get the overall integral. As a simple example, let's consider a simple uniform function here, where if we're doing sampling on a uniform distribution, so this means that you've got an equal probability of selecting a point, in this case, between x1 and x2. In this case, the uniform distribution is rho of x is equal to 1 over x2 minus x1, so it's an equal probability between x1 and x2. In that case, the integral f can be estimated by, and then we've got 1 over that rho, so it becomes x2 over x1 divided by the total number of shots that we've taken, this tau max, and summing up over the functions evaluated at those zetas. And this gives us then an estimate of that integral f. Now, the accuracy of Monte Carlo depends not only on having a sufficient number of random numbers that are drawn, but having a very good random number generator. And at the very end of this lecture, I'm going to give you a very brief introduction to one method for generating random numbers, because computers, strictly speaking, cannot do randomness unless it's a quantum computer. So with a classical computer, we have algorithms that don't genuinely give you random numbers, but they can produce sequences that satisfy statistical conditions that will be sufficient representations of random numbers. Now, how do we apply Monte Carlo in statistical mechanics? Monte Carlo provides a means for calculating partition functions and ensemble averages in statistical mechanics. So for example, what if we want to calculate the expectation value of some property A in the NVT ensemble? The way that we would write that from statistical mechanics is that the expectation value of that property A would be integrating over all of phase space, the value of A multiplied by the probability distribution for that particular part of phase space. So it would be A times e to the minus energy of the system over KT, and then that gets divided by the partition function, which is just the integral over all these Boltzmann probabilities. That then ends up giving you the average value of A. Now, with Monte Carlo, we're going to represent these continuous integrals as instead being summation over all of these sampled points from the Monte Carlo sampling, where we are sampling from tau equals 1 all the way to tau max. And for each of the samples, we've got the value of A for that sample times the Boltzmann probability factor, and then divided by the summation of the total Boltzmann probability factors. And this gives us a sampling of the integrals, and the more samples that we take, the closer we get to the actual value of the integral. So one of the other problems, though, is in sampling the right part of the phase space. So if we have the probability function here, e to the minus energy over kt, the parts of the phase space that contribute a lot more to this integral are the parts of phase space that are lower in potential energy. So if you're spending all your time sampling parts of phase space that the system never sees or very rarely sees, you're missing out on the more probable parts of phase space that correspond to more favorable regions of energy. And so what we need to do is to figure out a way not just to do the sampling just randomly over phase space, but to do that sampling in an intelligent fashion that biases the sampling towards the regions of phase space that contribute more to the integral. So that is just a more effective use of our computational time. And the way this is done is using an approach called importance sampling. So importance sampling techniques choose random numbers from a distribution that allows the function evaluation to be concentrated in the regions of space that make the most important contributions to the integral. So with statistical mechanics, the most important contributions to this integral are in the regions where the system has a lower potential energy. So what we want to do with our Monte Carlo sampling of the system is to bias it towards those regions which have lower potential energy, since those are the more favorable, i.e. the more probable configurations of the system. And the way that we're going to do that is by constructing what's called a Markov chain of states. And this was a solution that was developed by Metropolis. And this Markov chain of states is a sequence of trials that satisfies two conditions. First, the outcome of each trial belongs to a finite set of outcomes, which is called the state space. Second, the outcome of each trial depends only on the outcome of the trial that immediately precedes it. So in other words, it has lost memory of anything before the immediate predecessor of that state. So the next state that's chosen comes from a finite set, and it only depends on your current state, not on any history. And that's really key to setting up this Markov chain. So the two states then, the current state and the next state, are linked by a transition probability of going from some state M to some state N. Now, the Metropolis method, there's a picture of Nicholas Metropolis, is to use this Markov chain method where a new configuration of atoms is randomly chosen by making a step from the current configuration. So we have some current configuration of atoms. We're going to make a step away from that current configuration. If the potential energy decreases, then the new configuration is always accepted. If the potential energy increases, then the new configuration can be either accepted or rejected, and it's done so randomly following a Boltzmann probability distribution. So this is what this looks like mathematically. If we start off here at our current position, and this is the current energy level here, labeled as 0. Now, if we were to choose a new configuration of atoms, so we've got our current configuration, we're going to change that by going to a new configuration. If that moves downhill in energy, that is more energetically favorable, that would mean that the delta U is negative. And if the delta U is negative, we're moving in the downhill potential energy direction, which is favorable. That move is always accepted. And when that move is accepted, that means you move the configuration of atoms to that newly proposed configuration, and then you take another Monte Carlo trial step based on that new configuration. On the other hand, if the potential energy goes up, we don't just automatically reject it, but we would reject or accept the move based on the Boltzmann probability function, which is the intrinsic probability function built into statistical mechanics. So if the delta U is greater than 0, then what we have here is this probability function, which is the Boltzmann probability function, e to the minus delta U over kt, which looks something like this. So as the delta U increases here, this Boltzmann probability function is decaying. Now, what we do is draw a random number between 0 and 1. And if that random number falls above this Boltzmann curve, then that move gets rejected. If the random number falls below the Boltzmann curve, then this gets accepted. So if the move gets accepted, then that increase of potential energy is deemed to be acceptable. And so the system moves to that next configuration, and then it would undergo another Monte Carlo trial displacement based on that new position. If, however, the if the new configuration is rejected, then we would return to the initial position and try a different random move. So the way that Monte Carlo works then is that you do this sequence of random moves. Following the Markov chain of states, the next positions of the atoms that you choose depend only on your current positions. And following this Metropolis method, you would either accept or reject that new configuration. If you accept it, you change the system to that new configuration, and you try another step from there. If you reject, then you go back to your previous configuration and then randomly choose another trial configuration and then perform the accept or reject based on that. And then this will continue over any number of trial displacements that are made. And as the system progresses, what you're doing is actually sampling the configurational phase space following the Boltzmann probability distribution. So because the Metropolis method builds in this Boltzmann distribution of e to the minus delta u over kt, that means we are sampling the phase space exactly following this Boltzmann distribution. So the statistics of the sampling are the same as the statistics of the sampling in the formal statistical mechanics because they're both following a Boltzmann distribution. Now, this is a different way of sampling phase space compared to molecular dynamics. If we have a potential energy landscape, for example, shown like this, the way MD works is by integrating Newton's second law of motion. So we're integrating F equals ma. Unless you have some thermostat in the system, this is natively in the microcanonical ensemble, which means that the total energy is a constant. What you're seeing here is that as this goes up the walls of the potential energy well, you've got more potential energy that gets converted to kinetic energy as it goes down in the bottom, and the total energy is conserved because it's just obeying Newton's laws of motion. With Monte Carlo, what happens is that we make random moves of the system. With these random moves, we're able to explore more of phase space. We're able to randomly bounce around and overcome some of these barriers more easily. If we go downhill in energy, the moves always get accepted. If we go uphill, they could be accepted or rejected based on the delta E, so how much the energy is changing, and then the temperature of the system. If you're at high temperatures, you're more likely to accept unfavorable moves in energy. If you are at low temperatures, then you're less likely to accept those moves. So to compare some of these differences between MD and MC, with MD, we are exploring phase space by following the trajectories of the atoms following F equals MA. In MD, the particles have both positions and momentum vectors. So three positions and three position coordinates, X, Y, and Z, and then you've got X, Y, and Z contributions to the momenta. So if there are n atoms, that means there are 6n dimensions, 3n for the positions and 3n for the momenta or velocities. MD simulations integrate over time, and they're collecting information as the system gets integrated over time, and they are capable of predicting time-dependent properties. However, MD is not guaranteed to find a global free energy minimum regardless of the number of time steps, because it's not sampling in the same way that statistical mechanics samples the system. With the Metropolis Monte Carlo approach, the atoms are exploring phase space via random moves according to the Markov chain. The particles have positions, but there's actually no momenta here. There's no need to have velocities. It's not actually included in part of the method. So the system has 3n dimensions, only positions vectors, X, Y, and Z positions for each atom. The velocities aren't even included. And the information here, instead of integrating over time, it's integrating over ensembles, using importance sampling to predict the states of lowest free energy. And in fact, Monte Carlo sampling, because of sampling following that Boltzmann distribution, is guaranteed to find the global free energy of the minimum of the system, given an infinite number of steps. So this is one of the intrinsic differences between Metropolis Monte Carlo and MD, is that MC drives you towards the global free energy minimum, and MD doesn't necessarily do that. Another advantage of the Monte Carlo approach is that it's easier to adapt it to different types of ensembles. If you wanted to go to an NPT ensemble, for example, there are two different types of random trials that are done. There's the random displacements of the atomic coordinates, and then you can change the volume of the simulation cell by scaling the dimensions of the atoms. So having either random particle displacements or random changes to the simulation volume, and then you would reject or accept or reject volumetric changes based on what is happening to the enthalpy of the system. Monte Carlo is also easier for doing open systems, so you're not restricted to a constant n. For example, if you want to do the grand canonical ensemble, the mu VT ensemble, here the chemical potential is fixed while the number of particles fluctuates. So here we need to either insert new particles into the system or extract particles from the system. So in this case, one of the Monte Carlo trials is the insertion of a new particle or the deletion of an existing particle. So you could randomly either select a particle to eliminate from the system or randomly insert a new particle. And this particle insertion or deletion is accepted or rejected according to the probability in the grand canonical partition function. This is still a computationally complex problem because for dense systems, the probability of finding a good place to insert a particle can be quite difficult. So there are methods that have been developed to kind of bias that sampling, to kind of build some important sampling into the locations of where particle insertions may be most likely. But this is much more straightforward to do in MC compared to MD. We can also go to the Gibbs ensemble, which is the mu-PT ensemble. The Gibbs ensemble is used for calculating phase equilibria. And with the Gibbs ensemble, there are three types of possible moves. So this is a constant chemical potential, meaning it's an open system. It's a constant pressure, so the volume can change, and it's a constant temperature. With a Gibbs ensemble simulation, you've got two different phases here, and we're going to find the equilibrium between those two phases. Phase one is shown here on the top, phase two on the bottom. And there are three different types of moves that can take place in the Monte Carlo simulation, and these are done randomly. There is the particle displacement move, where you take an atom position and you randomly move it to a new position and see if that should be accepted or rejected. Then there are the volumetric changes where you change the volume of the system, as shown here. Or there are particle transfers, which involves taking an atom from one phase and then sticking it into the atom of the other phase. So for example, grabbing an atom from this phase two and sticking it into phase one, or the opposite. And basically, once you find the equilibrium here, with the Gibbs ensemble Monte Carlo method, you found the equilibrium between those two phases. Now, one of the drawbacks of Monte Carlo is that the Metropolis Monte Carlo technique itself doesn't actually have time. And since this is a kinetics course, we want to find a way to incorporate time into Monte Carlo simulations. And the way to do that is called the kinetic Monte Carlo method. And this is a really powerful method because this can reach, in many cases, an arbitrary time scale. It's not limited in time scale like standard molecular dynamics simulations. So kinetic Monte Carlo is a method of incorporating time into Monte Carlo simulations and achieving long time scale simulations. What we do is we start from our initial state here, I, and then randomly select from a choice of different transition states. So if there are, say, 4 different transition states available, that would lead to some various final states here, J. Going from this initial state, we have 4 different transition rates depending upon the activation barriers that need to be overcome. Then what we're going to do is randomly select one of these transitions to take. We're going to propagate the system over the transition barrier to the state on the other side. And then we have a time variable that starts off at 0. And every time we make one of these steps, we propagate the time forward according to the expectation value of the transition time. So instead of having a time step in MD that's fixed, so with MD, you've got a very short time step of on the order of 10 to the minus 15 seconds, which is fixed throughout the simulation. Here, the time step is governed by the expectation time of overcoming a transition barrier. And the jumps that we take in time correspond to the times that are expected to overcome that barrier. So it takes much larger steps in time. They may be non-uniform steps in time because you could have different expectation times for overcoming barriers depending upon the size of those barriers and the temperature of the system. There are different ways to implement the kinetic Monte Carlo algorithm. I'm going to show you one way here, which comes directly from the book. So according to this method, what we do is we initialize the system time to t equals 0. So we start off at 0 time. We perform a local minimization of the potential energy or enthalpy of the system to begin at the inherent structure configuration within that local basin. So we're starting at a local minimum in potential energy or enthalpy at time t equals 0. Then what we need to do is to find a set of possible transition points from that starting configuration. In our energy landscape chapter, we covered methods for finding transition points in an energy landscape, such as the eigenvector following technique. So we would use a technique such as that in order to get a set of possible transition states from that given starting configuration. Then, based on that set of rates, we're going to use transition state theory to give us the set of rates, the Kij's that are associated with that. And then we're going to calculate the total reaction rate by summing up over all of those rates. So we've got a K total, which is the summation of the rates going from our starting configuration I to the possible barriers here, J. So the Kij are the individual transition rates from the current state I to each of the possible next states, J. These transition rates are calculated from transition state theory, as we did in the energy landscape chapter. Now, the next step is that we generate two random numbers, R1 and R2, from a uniform distribution between 0 and 1. Now, we're going to randomly pick which transition pathway that we're going to take using R1. So this R1 variable is going to be basically position us somewhere. It's going to select out one of these transition pathways to take, which are weighted by how fast the rate is. So if you've got something that is a lower barrier, the lower barrier becomes a faster rate. That faster rate is more likely to be selected compared to one that has a slower rate or a higher barrier. So what we have here is a ranking of all these transition rates. The rates that are faster correspond to the lower barriers, and they are more likely to be chosen. And the probability function that is used to govern that is, of course, the Boltzmann probability factor that governs transition state theory. So we randomly pick one of these transition pathways. It's weighted according to the Boltzmann distribution. Then we actually execute that transition. So we move the system over the barrier and into the minimum on the other side of the barrier. Then what we do is advance the system clock forward by a time step, and that time step is given by this -1 over K total times the natural log of R2. And so there's kind of a randomization that is built into the time step here based on looking at an average of all of these rates. Then this gets repeated until you've achieved the total simulation time. So randomly, from the new point, you find new transition barriers, randomly select one of them, go to the next position, propagate the time clock forward. Now, in this particular method, the time clock is propagating forward not based on the particular barrier that you've chosen, but based on kind of an average of those barriers with some randomness built into it. And another alternative way of doing kinetic Monte Carlo, you would use the expectation time for that specific barrier that is chosen. Statistically, in the limit of a large number of steps, you would end up getting the same result. Here is an example of doing some kinetic Monte Carlo simulations. This is for an additively manufactured metal. This is in a paper from Rogers et al. In 2017. And what they have here are grain structures that have been calculated through a kinetic Monte Carlo simulation and compared that to the grain structures from experiments. You can see similar types of structures here. And what they've done is to incorporate the material conditions, the process conditions, used kinetic Monte Carlo to get the evolution of these grain structures, and then successfully validated that with experiments. Another example of kinetic Monte Carlo due to Kroos et al. From 2018 is in the plasma-enhanced CVD, chemical vapor deposition of amorphous silicon thin films. And here you've got a growing thin film, and this is growing from deposition of atoms from some supersaturated vapor. And there are different fundamental events that can occur, these 4 elementary events in the kinetic Monte Carlo simulation. There is a bulk lattice atom, so like a bulk silicon atom here. This is in gray. You've got the hydrogenated surface site here, which is the open one. Dangling bond sites, which are the sites with the diagonal lines through it. And then physisorped radicals, which have an R in them. And then the elementary events that can occur are migration of the hydrogenated surface site, so movement along the surface here. Physisorption, which would be taking this radical here and adsorbing it onto the surface. Chemisorption, which takes this physisorbed radical here and brings it to a dangling bond here to form a chemical bond between the two. Or you can have release of the atom from the growing thin film, or in this case, going from the thin film into the gas. So all of these are events that can occur. They all have their associated barriers. And using Kinetic Monte Carlo, you would randomly go through and show how these amorphous silicon thin films are grown through this random combination of all of these events. Now, Monte Carlo involves a lot of random numbers. Random numbers are used to generate new configurations of atoms. They're used to select what event you do, whether it's a position change, volume change. They're used for selecting which pathway to take in Kinetic Monte Carlo. They're used to decide whether you should accept or reject a move. All of Monte Carlo rests on having a good random number generator. And as I mentioned, classical computers are incapable of truly generating random numbers. And so what we need to do is have an algorithm where the computer can mimic the generation of random numbers. And these are called pseudo-random number generators. And most of these pseudo-random number generators are designed to produce a different sequence of numbers if a different seed is provided. So you provide like the initial seed to the random number generator, and then it produces a sequence of numbers based on that seed. And normally that seed is kind of randomized by choosing something like the specific time or the date. Like if you take the system clock on the computer and use the time and use that as the seed, then each time you run the program, you'll get a different sequence of numbers. So a different sequence of pseudo-random numbers. A common method for generating random numbers is called the linear configurational method. And in this case, what we do is we start off with our seed. So this C here is our initial seed, and we're going to generate a sequence of random numbers based on that seed. And what we do is we take that seed or the previous number in that sequence, and we generate the new number here. So C of I is going to be equal to taking the previous random number, multiplying by a constant, adding a constant, and then doing something which is called modulo division, which is just doing integer division and then taking the remainder, because the remainder is something that's a lot more random than the quotient itself. So this mod here means that we take this number here, divide by m, and then take the remainder. And that remainder becomes the next number in the sequence. And then we continue this process using that same type of algorithm to generate this whole sequence of pseudo-random numbers. And there's lots of techniques for trying to optimize and test how good random number generators are. So to summarize, Monte Carlo is a simple and versatile technique for integrating arbitrary functions. We need to use importance sampling to bias that sampling. So we can bias our random sampling towards the configurations that contribute the most to the integrand. The Metropolis method is one implementation of that, which is based on generating a Markov chain of states. The Metropolis Monte Carlo method is easily extended to other ensembles, and we can incorporate time using Kinetic Monte Carlo. With Kinetic Monte Carlo, we can access much longer timescales compared to MD simulations. All right, that is it for this lecture. If you have any questions, please let me know, and then I will see you next time. Thank you.